Greetings, class. Welcome to week 2 of operating systems. We made it through week 1 very successfully. And now let's dive into week 2. Okay, in week 2, we're going to be talking about processes and process management and how the operating system schedules that information through the CPU, the central processing unit. Okay, and we'll talk about well, let me back up. Processes are the main function, okay, of the operating system. It is how we get everything working. And if you think about the thousands and thousands of processes that are happening simultaneously in a given computer, then you know that the operating system has a job. The bulk of that is keeping track of processes, where they are, what status are they in, and basically, are they finished? Are they completed? I mean, are they still waiting? Are they blocked? Okay, so that's the main process engagement that has to be done by the operating system. So that's what we're going to talk about today. How do we manage that? How do we schedule so the processes actually run more efficiently? And so let's start in. Let's jump into week 2. Okay, in week 2, looking at the overview of the content of what we're going to be talking about in week 2, it is process versus threads, the process life cycle, process control blocks, okay, context switching, CPU scheduling, multitasking and multi-threading, okay, process monitoring tools, and then the hands-on review will be done in class and as part of your assignment. And in week 2 is really the lab 1. Okay, we kind of explained that in class last time, but we'll be basically looking at 2, 3, 4, 5, 6, 7, and 8 as far as how the operating system manages processes. Okay, so in looking at that, okay, so let's take a look. Let's look at processes versus threads. Okay, a process is a program in execution. Threads are the smallest unit of execution within a process. So if you look at a process, you got the process code, we got the data, and we got the resources. All those are in its own address space. So we keep all those things related to the process together. It creates a process. Creating a process is a resource intensive. It takes a lot of work and a lot of memory in order to maintain the status of a process. Now, if you look at threads, threads are shared process code, shares process data and resources. And each thread has its own program counter, excuse me, as far as where the program is executing. It has registers, it has stacks. Okay, creating switching thread is lightweight. A thread is part of a process. Okay, so if you see in this example here, okay, we have process, we have thread 1, which is using code. We have thread 2, which is just handling some data. We have thread 3, okay, which is handling resources. So we got all these look like pieces of the process that are running at the same time. And those are called threads. They're running independently, but they're running in parallel. Okay, so that's the concept of the processes versus the thread. The process is the big item. The threads are the little items that are basically running simultaneously. Okay, process life cycle. The process life cycle basically is new, ready, running, waiting, or terminated. Okay, new means I'm emitting the process into to be put in a position where it's ready to run. It's not outside. It's ready to go. So we're in a new emit status or cycle. Then we have dispatch. Dispatch says I'm going to go ahead and start running it. So my processes are running. Okay, everything's fine. There might be while I'm running, it hit a situation where I have to wait for something. And that's in this case where we go from running to waiting, and it's blocked. Blocked means there's something that's holding me up and preventing me from running my process. Okay, so it's going to wait there for some time, either waiting for an IO event or a complete event, okay, or access information which falls under the IO. So I'm running until I get the block satisfied. Once I get the block satisfied, then I'm going to go back and say, now I'm ready to continue on. Okay, when the operating system says it's ready to go, it'll put me back in running status, and then I'll go ahead and run, hopefully not getting blocked again, but going into a termination status that says I'm finished. So we look at that, we got new process being created, ready, the process is in memory and ready to run, waiting for the CPU. The central processing unit. Processing is waiting for an event to complete if I'm waiting or blocked, and terminated, the process is finished execution. The key takeaway here is the operating system manages movement of processes through states to ensure efficient CPU utilization. Okay. CPU operating system. CPU is the program that's actually doing all of this execution. The CPU executes. Okay. The operating system executes on the CPU. Okay. The next thing is the process control block. This is probably the most important piece of real estate, okay, in the whole computer. Okay, because with all the processes that we're executing, we have to keep track of them. The way we keep track of processes is through the process control block. The process control block is a data structure used by the operating system to store information about each process. Such things as process ID, process state, CPU, the registers for the CPU, the program counter, the scheduling info, memory info, IO, anything related to the process is in the cross-process control block. So if a process goes into a wait state, process control block is updated. If a process started, okay, it adds it to the process control block. Okay, so all this information, okay, is basically kept in that particular entity. And I was waiting when I was going to do that because I do it. Okay, so that's what as far as the process control block. Okay, the contents, identification, you can have a process ID, a parent process ID, user ID. These are just the various things that can be used to keep track of, that might be kept track of by the process control block. The process control block in the operating system are stored in process tables. The operating system uses these tables to keep track of all processes to perform context switches. Context switches is I'm going from one state to another state. That is a context switch. Okay. The process control block is essential for context switching, tracking process information across its entire lifetime. Process control block. Context switching. Okay. A little more detail on that. A context switch allows the operating system to switch the CPU from one processor thread to another. I have one process, put it in the process control block. Okay. It goes into a wait state, waiting for IO. CPU says, okay, I'm going to switch that to now I'm operating on another process. Okay. Okay. So that's what's basically designating here. Okay. I save the state of the current process in the process control block, load the state of the next process. Okay. Update the memory management structure if needed, transfer the CPU control to the next process. I'm switching context. Here we got process A is running. Operating system does a context switch, and that switches me to process B. Okay, process B will no longer be running. I switch context, and I go start on process B. Okay. Why it matters, it enables multitasking and time sharing. ensures fairness among processes, and allows the operating system to respond to interrupts and IOs. Again, it's the way that the operating system kind of controls what's running, what's not running, what's running, I need to run. How do I give it control to go ahead and run? Basically taking what was running and putting it in a wait state. So that all that back and forth as far as when a process is executing is basically based on that context switching. Okay, context switching overhead does exist. Okay, context switching takes time, uses CPU cycles. Too many switches can reduce the system performance. Key takeaway here is context switching is fundamental to multitasking. Okay, but introduces overhead when it must be minimized. And again, multitasking, we're going to talk about that, but running multiple tasks at the same time, even from different processes, is switching things back and forth. Yeah, this switching things back and forth allows me to run one process, one piece of a process, stop, run another piece of a different process, stop, run another piece of a 50th process. You know, sharing that information, sharing that cycle to the point where I can basically run multiple processes at the same time. Okay, so with that, let's just jump into 7, then we'll come back to 6. Okay, as far as multitasking versus multi-threading. Multitasking and multi-threading lets the operating system runs multiple activities at the same time. Multitasking, operating switches CPU among multiple processes. Each process has its own address space, resource, improved CPU utilization, and responsiveness. For example, editing a document while streaming music. Okay. So I'm taking that information. Here I have process 1, process 2, process 3, process 4. Okay, CPU time is changed. So I'll give part of process 1 an opportunity to execute for a little while. Then I'll switch it to process 2. Then I'll switch it to process 3, process 4. So I'm multitasking. Okay, I'm running multiple tasks at the same time, basically sharing the address space. And multi-threading says multiple threads exist within the same process. Multi-threading says I have a process and I have it structured so that I can run part A of process 1 and part B of process 1 at the same time as 2 different tasks. Okay, or 2 different threads. Okay. Okay, so here that's what it's saying. Multi-threading exists within the same process. Threads share code, data, and resources. More efficient communication and switching. Example, web browser, multiple tabs. So within this one process, I have tasks or threads being executed simultaneously for the same process. The code is structured so that I can run multiple threads of that particular process. That's an architectural design that I can put into programming. Okay, here benefits, better CPU utilization, improved responsiveness, higher throughput. The key takeaway here, multitasking allows multiple programs to run at once. Multi-threading enables multiple threads within a given program to run concurrently. Okay. So one is multiple processes, one is multiple pieces of a process that are running at the same time. Okay, CPU scheduling algorithms. This is basically, in looking at how we might spread the love of these 4 processes. Things that we can do, we can use the algorithm that says it's a first come, first serve. Processes run in the order that they arrive. Okay. And they're basically executed until they complete, unless there's some sort of interrupt. SJF, shortest job first. I have a series of processes that I have to run. Okay, I have an estimate of what it's going to take each process to run. So I'm going to take the shortest estimation and let it run first. Okay, so that's shortest job first. And so basically that allows the system to basically quickly perform processes because we know that they're not going to take a lot of time to complete. Round robin. Round robin says I'm going to give equal opportunity for process 1, process 2, process 3, process 4. Round robin says I'm going to go to process 1. I'm going to let it execute for 10 seconds. Then I'm going to go to process 2, let it execute for 10 seconds. Process 3, that's round robin. Just in order, I'm basically letting each process in a round robin fashion execute until completion. Priority scheduling. This is I have I introduce a process, and it is a process priority. I need to finish this process. I need to give it higher priority. In that particular case, a process comes in, is flagged as being prioritized. And if it was there, I'm going to give it the opportunity first to execute. Then we have multi-level queue. Ready queue is divided into separate queues. Flexibility, easy. I was just saying I have 10 items. I'm going to put 3 in Q1, 3 in Q2, 2 in Q3, and then I'm going to manage the queues. Okay, as far as what executes. I'm not really looking at the program level, but I'm looking at the queue level. And then the multi-level feedback queue, processes can move between queues. Okay, I can have priorities or first come, first serve among the 3 queues, but I also have the capability of taking something out of Q1 and putting it in Q3 and still manage based on queues. So that's what's based the multi-feedback queue. Schedule criteria impact, CPU utilization is maximized, throughput is maximized, turnaround time is minimized. Okay. Key takeaways: scheduling algorithms affects performance, fairness, and system responsiveness. No single algorithm is best for all situations. Key point. Okay, so 8, processing monitoring tools. How do I monitor what's happening with all these processes and what I'm doing as far as scheduling and as far as updating the process control block. Here, that's basically looking at it's being done by Windows Task Manager. You can take a look at that now on your laptop. Okay, as far as doing I think there's a control. Well, it depends on the model, but you can hit a control task manager that will bring up the manager, okay, on your keyboard. Resource monitor, okay. Windows has a resource monitor, performance monitor. All those are accessible via your laptop. Linux, okay. Linux has the same capabilities, HTOP, PS, okay. Process snapshot, interactive process viewer. Then this is basically giving you the capability to take a view and take a look. And that's that is one of the items that are in your lab, is to be able to look at the processes that are running on your laptop, and you'll be using, for those that are using Windows, you'll be using Task Manager. Let's see, what can you monitor? You can monitor CPU usage, memory usage, disk I/O. Yeah, anything that's related to a process, you can monitor. Key point: monitoring tools help you observe how processes use resources. You can have a process that for some reason has been given priority and it's using 80% of the resources, which means nothing else is running. Okay. This gives you the capability to review those processes and taking that information and utilizing that in order to troubleshoot. Okay, so that's week 2. Again, be prepared for your quiz, okay, on Tuesday. I think the assumption is you would have already looked at this before then. Okay, so with that, we'll be, again, going over the homework and assignment, and jot down any questions. I mean, that's one of the key things. If there's something that you don't quite understand, jot it down and we'll work through it together. Okay, thank you, everyone. See you in week 3 or see you in class on Tuesday. Have a good one. Bye.